Good afternoon, everyone. I apologize for not being to give you a lecture on Monday due to some reasons. But anyway, so here I am. So today we are going to move to another section. But before we move to another section, let's have a quick recall about what we have learned last week. Okay, and this will be the material will be the questions in the Kahoot today. Okay, so please let's do it right now. So first of all, last week we talked about processes, right? Okay, when we talk about processes, and then we think of the what is the unit and dimensions. Okay, so but before unit, we know we have a volume. So everything has a volume and unit. For example, 2 centimeter. 2 is the volume. Centimeter is a unit, right? So what's the difference between centimeter, meter, or kilometer? So they belong to the same dimension, but they have different units. Okay, so unit A, unit B, and unit C. For example, like centimeter, millimeter, or kilometer, but they all belong to the same dimension. Okay, so there are two types of dimensions. The one is that you can measure you can measure it. That's called dimension. Or it can be calculated. Okay, so this is the two type of the dimensions. Okay, so that's what we learned. So the first key point you need to know is volume, unit, and dimension, right? Okay, and then after that, we need to know what's the conversion factor and what's the dimension equation. So conversion factor means what? Means how do you convert centimeter to millimeter? Or how do you convert a centimeter to kilometer? You need a factor, which is the conversion factor. Okay, so the following section will tell you how do you convert kilogram to pound. Which one? The one is SI system, one is American engineering system. So these two units also need a conversion factor, so that you will be, if you know the conversion factor, it will be easier for you to transfer one number to one unit to another unit, and just that you change the numbers. Okay, so once you do the calculation and using the conversion factor, you need to do it as an equation. So this kind of equation, we call it dimensional equation. Okay, so I'm sure I have explained it to you. This is what we know about it. This is what we call dimensional equation, right? So I don't want to waste your time here. So just let you know this. So the components of a system of units, there are three types. First type is called base units. Second is multiple units. The third one is divided units. Okay. So you need to notice this is what we know about base units. There are 7 only. There's no number 8. Okay. SI base unit, there are seven base units. I want you to remember this very well. Okay. So what's the voltage? Express the voltage using the 7 SI base unit. Can you do that for me? Yes, you can, because I explained this to you last week. Okay, can you express the ohm, the resistance using the 7 SI base unit? Can you do that for me? Yes, you can, because that will be easy, because you know V equal to I times R, right? V is voltage, I is current, times what? Resistance. Okay, so this is easy. Right, and here is that you have many American engineering system and SI system. How do you do the conversion? And of course, we call it conversion factor. And these are some basic knowledge you need to know. First of all, is the length. You need to know what's the length from centimeter to inch. Okay, and what's the kilogram to pound? So what's the Celsius to Fahrenheit? Okay. Okay, and this is an example to let you know that the importance of the conversion factor. Otherwise, you will have a big trouble when you do the conversion. Right. So this is all we learn, and we also learn this. How do you know the definition of the force and definition of the weight? And we also know that that's related to what? The mass and the weight is related to what? Gravitational acceleration, right? Okay. So you need to know the different. You need to know the numbers of the gravitational acceleration using different systems. Okay, like American system or SI system or CGS system. Right. So that's it. That's all what we have learned last week. So I hope you know this very well. And today, let's move to a new topic, which is the section 2.5, numerical calculation and estimation. This is very basic for engineers, not only for chemical engineers, but also for other engineers, okay? Chemical, electrical engineer, mechanical engineer. Anyway, so how do you, when you get a number, how do you do another number? How do you get another number? How do you calculate these numbers? And when you get a number, you get an answer, how do you estimate the answer is right or not? So, first of all, let's start to learn three terms. The first one is called scientific notation. This is, in Chinese, is 科学符号. Okay, scientific notation. The second one, significant figures. Significant figures, 有效数字. The precision is what? How good is the number you calculate? What's the precision, 准确度? Okay, so first, let's start to learn these three terms. The first one, why we need scientific notation? So if you have a very big number, for example, if you have a number which is 1, 2, 3, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, is it so stupid to write number like this? Yes, right? I don't want you to write number like this. You are not professional. And you don't want to write this because this wastes your time. So how can you express this number? And this is the way to express this number. Is 1.2, 1.23 times 10 to what? 15th. This is easier compared to this one, right? So I'm sure you want to write down in this way. And what is this? This is called scientific notation. Scientific notation. So the definition is what? The definition is this number need to be between 0.1 to 10. So you might say, well, Professor, can I write down something like this? 0.123 times 10 to 16th. Yes, you can. There's no problem. Okay, as long as it's not beyond 0.1 to 10, that'll be fine. Okay, that'll be fine. But basically, normally for general purpose, normally you write down something like this. This is between 1 to 10, or between 1 to 9, 9.999, something like this. Okay, so let's think in this way. How about this? This is a very big number, and next one is a very, very, very small number. So I'm sure you want to write down in this way, 2.8 times 10 to minus 5. Okay, this is number. So this is a volume. So this is what we call scientific notation. It's easier for you to write down and to tell people the number. And people will be easier to understand the number, right? Okay, the second term is called scientific notation, significant figures. Significant, what is this? Let me make an example for you now. Assume we have a balance. You know what is balance, right? You put some samples on the top of this balance in this plate, in this tray. And you got a number here. this digital number, right? Okay, so once you put some powders on the balance, you got a number. For example, number tell you is 1.23. Why? You might say, wow, Professor, why is 1.23? Because they are, can you see that? This is 1, 2, 3, 4. There are 4 digital numbers. 4 digital number. One is become a decimal, right? This is called decimal point or decimal, okay? Decimal point here. So below, beyond the, on the right side of the decimal, that's 2.23. So there are 2 digital numbers on the right side of the decimal point. Okay, so the smallest weight, so smallest number you can get is the 2 numbers in on the right of the decimal point, right? Okay. However, if you put the same amount of the sample to this balance, and you understand there are 1, 2, 3, 4, 5, 6. There are 6 digital numbers on the right side, on the right of the decimal point. And of course, you understand which one is more expensive, these 2 balances. If you want to buy a balance, which one will be costly? You spend more money to buy. Which one? Right or left? If I give you 0.5 point, will you answer me? Raise your hand. Do you understand what I mean? If I give you 0.5 point and you tell me which one you want to buy to get, if you need to spend more money, do you want to answer me? And if you get my answer right, I'll give you 0.5. Raise your hand. Yes. Left. You will spend more money or less money? Less money, right? Okay, thank you. That's correct, right? Actually, this is not a difficult question. This is very easy. I just want to test whether you have guts to raise your hand or not. Obviously, not many of you have guts, right? Okay, don't worry. If you got the answer wrong, you lose nothing. You lose nothing, right? So I want you to work with me. I want you to learn happily. Okay. So of course, obviously, you spend more money to buy this balance. But what? But why you want to buy this balance? Because this one give you more numbers on the right side of the decimal point. That means what? This balance give you more precision, right? You might get 0.231313, for example. So you get more numbers. That means what? This has more precision. Okay? Of course, you want this. But if you don't have money, you better get this. Right. So the third term is called significant figures. What is significant figures? If I give you this number, first of all, let's have a definition of the significant figures. So if this number has a decimal point, and the definition of the significant figure is that to count from the first non-zero digit on the left to the last non-zero, zero or non-zero number. I'm sorry I speak in English, but I'm sure you can read this in Chinese. Right? There's no problem for you to understand. Let me give you an example. So if I give you this number, I want to ask you what is the significant figure. Significant figure sometimes means precision. Okay, so let's think it this way: 0.00340. How many significant figures? From the first non-zero digit on the left, count from here, is 0, right? Skip, 0, skip, 0, skip. Wow, this is the first one, non-zero number, right? Non-zero digit. We start to count. 1, 2. Can you count this? Yes, you can. This is 3, right? Because this is the last one, which is 0 or non-zero. So you can count this. So the significant figure is what? 3. Okay? How about this one? You count from this, skip, skip, skip. 1, 2. So what does it tell you? Significant figure is what? 2. So you might tell me, Professor, these two numbers tell me the same thing. Am I right? It's all 0.0034. Right? 0.0034. But when you think of the weight, and you put this, you get this number from a balance. So which one get you more precision? Which balance is better? This one or this one? Which balance is better to give you better precision? This one or this one? Left, right? Thank you. Thank you. So you have 5 digital numbers in this balance, and you only have 4 digital number in this balance. So although it tells you the same number, but it tells you the different things, different significant figures. Okay, how about this one? 50.00. The significant figure is what? 4. Because you count from the first one, 5, right? 1, 2, 3, 4. Because you have decimal point. That means what? The balance has 2 digital numbers on the right of the decimal point. Okay, if there's no decimal point, how do you calculate the significant figures? Again, you count from the first non-zero and to the last non-zero. So it's non-zero, non-zero. Let me give you an example. So how about this one? 478900. How many digital numbers? How many significant figures? 4, right? Because you count from the first non-zero. 1, 2, 3, 4. Can you count this? No, you cannot. Why? Because this you need to count the last non-zero number. So this one tells you you have 4 significant figures. And how about this one? You have the first 3, you have first 4 digital numbers the same. 4789, 4789, right? But you got 1, 2 here. So how many significant figures? 1, 2, 3, 4, 5, 6. You have 6 digital numbers. You have 6 significant figures. So what does this two tell you? If you, in terms of the balance, what does these two numbers tell you in terms of balances? If you have this balance, the minimum number is 100, 100, 200, 300, 400, right? And this one, the minimum number is what? 1, 2, 3, 4. So which balance is better? But more expensive, of course. This one, right? This one. And this one can tell you you have 6 significant figures. You have better precision. Okay? Right. Let's practice a little bit. So please tell me the significant figures. How many of these? Raise your hand. Yes. Thank you. Of course, in your lecture, no, right? You got 0.5 point. Congratulations. 2. How many? Next one? Sorry, no more. Tell me, how many significant figures this one? 2, 3, 0, 0. There's a decimal point. How many significant figures? Yes. 4, right? Thank you. Why? You have to count from 1, 2, 3, 4. But this what does it tell you? You start to count 100 kilogram, 200 kilograms, 300 kilograms, and this count from 1 gram, 2 grams, 3 grams, 4 grams. Right? So significant figure is high. Okay, no more score, no more points. Okay, for now. How many? 5, right? 5. So you might say, well, Professor, can I use scientific notation to express this? Of course. If you use scientific notation to do this, to express this, you have to write down 2.3000. But when you think of this, you can think, well, the balances you use are different. Okay? How about this one? How many significant figures? 1, 2, 3, 4. Can we count this? No, there's no decimal points, so you have to count what? 4. If you use balance to think of this, I'm sure you'll catch the point very soon, very well. How about this one? 0.0352, right? Okay, how many? How about this one? 0.03500. How many? 4, right? Okay. Are you with me so far? Are you with me so far? Yes, right? Okay, good. So, what's the precision? The number of the significant figures in the reported value of a measured or calculated quantities provides an indication of precision with which the quantities is known. So, significant figures is related to what? Precision. Okay. So as I just told you, you have better precision using this balance compared to this one. Right. So 8.3, the significant figure is 2. So it could be what? It could be 8.25 or 8.34. Right? If you use round off, right? If you put this 5 and move to add 1 here, so you got 8.3. But if you remove the number 4, and if we remove 4 here, you got 8.3. That will be number 3. So the balances only show you this number, but it could be, in a reality, the weight, if you think of this number as a unit of weight. Okay, so it can be 8.25 gram or 8.34 gram. You can use gram, or you can use second, you can use centimeter, for example. Okay, how about this one? 8.300, significant figure is 4, right? So it could be 8.2995, or it can be 8.3004. Okay. So if the significant figures increase, that means what? Precision increase. Okay, compared to this one, you have the same number, but significant figures increase from 2 to 4, the precision increase. Okay, so how about 1 cow? What's the significant figures? 1 is a value, cow is a unit, right? You can have 1 cow, 2 cows, 3 cows. So what's the significant figures? Infinite, right? Because 1 is a precise. Okay, it's not measured. Okay, so a pure integer. This is a pure integer number. So the significant figure is infinite. An infinite number of the significant figure you can write down as 1.00000000. So the value is non-precisely. Okay. So next topic is, how are we going to, if we have numbers, like we have number A, number B, number C, number D, how can we do the addition, subtraction, multiplication, and division? And we have to do it in scientific way. Okay? Let me make this example for you again. So if you have 2 balances, and student A use this balance. Student B use this balance. And student A put A sample, which what he gets 45.31 kilo, 45.31 gram. That's student A using use sample material A or sample A. So student B, he has a sample B. So the sample B, the weight of the sample B is 1.23 1.236871 grams. And now a professor like me asks student A and student B to put these two materials together and tell me what's the weight of this A plus B. So can you tell me the answer? If you tell me this answer, I will kill you, right? I'll kill you. Why? Because I just told you, you need to find, you have to do it as an engineer, a professional engineer, right? So this is if you don't have this unit, this is 100% right. This value is 100% right. Why? Because for 45.31 plus 1.23, blah, blah, blah. This is the correct answer. But when you do the measurement, this is not correct. Why? Because I told you 45.31, it could be 45.304 or 45.05 or 45.314. It could be like this. So you don't know the number behind 1 here. So if you do the addition like this, obviously this is not the correct number you should show. Otherwise, you will have big trouble when you have the next number. You need to put the next number together. So the addition and subtraction is that we have some of the definitions. Okay, the definition is that if you see the last significant figures and you get the numbers and you do the runoff. Okay, so the rules for addition and subtraction concerns the positions of the last significant figures in the sum. You might wonder, wow, Professor, I don't understand why is this. So let me show you how are we going to do this. So please, as an engineer, you need to know this. Okay, now, well, if you are a scientist, you also need to learn this too. So how do we do addition and subtraction? For example, we have 1,530. We don't know the volume. We don't know the units, but whatever. How many significant figures here? Anybody want to tell me? How many significant figures here? 3, right? 3. Okay. Right, so I have another sample, which is 2.56. And I want to do the subtraction. So if you think of the weight, again, you have 3 digital number. This is significant figure is 3. The significant figure is 3. So when you do the subtraction, obviously this is number you can get. I'm sure you won't get the wrong answer. I'm sure you will get the right answer, right? But is this the number is this the final answer? No, this is not, right? Because if you think of, you measure the weight of one object, which is this number, and you also measure the weight of this number, which is object, which is this number. And you might think this might be not correct because it might be 15305 or 15295, for example. So what we can get is you have an error here. This is the last number of the significant figure, right? Okay, so this is the last number in this of the significant figures. Okay, and what you need to do is you choose this one. You choose this one. And the position of the last significant figures in the sum is this one. So the answer you will get at And the next number, you do a round-off. You do the round-off. Round-off means what? If its number is more than 5, you add 1 in the front. If the number is less than 5, like for example, like 4, 3, 2, 1, 0, you just remove it. Okay, so as a result, if you do the round-off, the answer you can get is 1530. Okay, so this is the answer. So you might say, wow, Professor, something strange. If I have 1,530 subtract 2.56, we got the same. This is the same number, right? This is the same number. And is this the answer? Yes, this is the answer. You know why? 2.56 is too small compared to this one. It's less than 1%. Okay, it's almost about 0.2% only. So you can regard this as an error because this can be what? As I just told you, 3, 0, what? 4 here. It can be 4 here. Okay? Or it can be 299 here. So this is the kind of error. So as a result, if you do the subtraction, the answer you can get is this one. Exactly the same. Okay? How about this one? I have 3 numbers. First one is 1.0000 plus 0.036 plus 0.22. So how many significant figures here? What? 5, right? 1, 2, 3, 4, 5. So last digital number of the significant figure is here. What's the last significant figure here? This one. What's the last significant figure here? This one. So when you use your calculator to do this to add up these 3 numbers, the answer you will get is this one, 1.2560. But this is not the answer you should give it to me. Why? Because if you do this, if you consider significant figures, then we only have this one will be the significant figures here. Okay? So this is the one. And you do the round-off after the digital number after 5. So if it is more than 5, and you have to add up 1 in the front, right? So the answer you will get is what? 1.26. So if you have these 3 numbers get together, all you can get is 1.26. Right? Okay. So this is the answer. How about this one? A little bit challenging, but I don't think this causes you trouble. So if I have a scientific notation, 2.75 times 10 to 6 plus 3.400 times 10 to 4. So how many significant figures here? 3, right? How many? 4 here. But we don't want to do this because this number is different. So for a scientific notation, this number is different. We need to put it the same. So we take out 10 to 6 here. So we have 2.75 plus what? 0.03400. Again, this is 4 significant figures. This is 3 significant figures. So why is the 1? What's the 1? Here, right? Here. Okay, so the answer we can get is this one. And then if we do the round-off after this, so the answer we can get is what? 2.78 times 10 to 6. Okay, so this is addition and subtraction. Okay, next topic. How do you do multiplication and the division? So the key point is the lowest numbers of the significant figures. If you have three numbers and you do the multiplication and subtraction, you take out the lowest numbers of the significant figures for your final answer. Okay, let me make an example for you. So 3.57 times 4.286. If you do your calculate this multiplication, and you using your calculator, you will get 15.30102. So this is not the number you want. So but you can see that how many significant figure here? 3. How many significant figures here? 4. So you have 3 here, 4 here, and you need to take what? The lowest numbers of the significant figures. So the number you can get is what? 3. So 1, 2, 3. This is the one. And after this one, round off. Round off. So 3, 4, and of course, you don't want to increase significant figures, right? This is 7 significant figures. You don't want this happen. So you need to do this. Round off. You need to get 3 here. So the first one, do the round off. So 15.3. Easy, right? Easy. Right, how about this one? 5.2 times 10 to minus 4 to times 0.1635 times 10 to 7 divided by 2.67. And use your calculator. This is the answer you got from your calculator. And then tell me the significant figure here. 2, right? How many significant figure here? 4, right? How many significant figure here? 3. So you choose the least lowest number. 2, 4, 3, obviously 2. So you have to do 1, 2. This is 1. So there are 9 significant figure here. Obviously, you don't want to get me this answer, right? So you will get 320. Why? Because A, you do the round off, you add 1 here. So that will be 1 plus 1 equal to 2. So 320. This is the answer. Okay? No problem. Easy. Piece of cake. Okay, so how about this one? 4 times 12 equal to what? 48. I'm sorry. Answer is 50. Why? You have 1 significant figures. You have 2 significant figures. And in the end, you need to get 1 significant figure. So 48, A, you have to do the round off. The answer will be 50. So you might say, well, Professor, I'm not happy with this number. I want to get 48. So how are you going to write the equation? I want to get 48. I want to get the final answer, which is 48. Can you write down the equation for me? No problem. As long as you have 2 significant figures for each one. So if you do this 4.0 times 12, you have 2 significant figures. The first number, for the first number, you have 2 significant figures for the second numbers. So the answer you will get will be 2 significant figures, right? So it's 48. No problem. Good. How about this one? Okay, so how many significant figures here? 2. How many of these significant figures? 1, 2, 3, 4, 5. There are 5. So you can get is this 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, right? So what you can get is what? You need to get 2 significant figures. Am I right? Right. So what can you do? The answer will be what? 300. But unfortunately, if you write down 300, how many significant figures here? So only one, right? Only one. But we need to express this answer as using two significant figures, right? Because this has a two significant figures. You cannot reduce significant figures on the equation on the right side of the equation. So how can you express this number using two significant figures? Scientific notation, right? So 3.0 times 10 to 2, that'll be two significant figures. Okay, so next week, if I give you the Kahoot like this, and your answer is this, I'm sorry, you don't get points, right? Okay, you need to know if you have two significant figures, when you do it, if you need to get two significant figures for your final answer, you need to express the numbers as a two significant figures. Right, so the conclusion is 3 terms, please remember this well. Scientific notation, significant figures, and precision. And after that, you need to know how to do the addition, subtraction, multiplication, and division using significant figures. Right. Okay. So section 2.5b will be validating results. Okay. So next topic will be validating results. How are you going when you do the calculation, you get a number? How are you so sure your number is right? So how are you going to validate the number, the result you got? So every problem as an engineer, your job is to solve the problems. No matter it's mathematical problem or physical problem or chemical problems, your job is to solve the problems. So every problem, you have two things you need to think of. First one is, how do I get a solution? How do I get the answer? Okay. The second one is, when I get an answer, when I get one, how do I know it's right? How can I validate the answer? Okay. So validating the results goes to 3. There are 2 basic directions to let you find out that the results. The first one is back substitution. The second one is order of magnitude estimation. The best substitution is that once you have a number, you just put the number back to the equation, and you see whether your answer is right or wrong. Okay, but this is time consuming. It takes a lot. It takes a lot of time. You might don't have much time for this, because the reactor is going to explode, right? You are going to get fire, or the building is going to get fire. You don't have time to do the lengthy calculation, and what you need is a quick answer, right? So the next one might be order of the magnitude estimation. For example, if your number is 27.36, you use 20 or 30, you put it back to the equation, and you simply think it's right or wrong. Okay, so this is order of magnitude estimation. As an engineer, you always need to think in this way. That will be easier, right? I'm sure you do this when you are in high school. And the third one is apply the test of the reasonableness. So, for example, you got the flow rate, and the flow rate is quicker than the speed of the light. It doesn't make sense, right? So you know the answer is wrong. So you don't think this is right answer. Okay. So there are some examples I want to show you. very soon, okay? So let's move to the 2.5C, estimation of the measure of values. This is sample means, average. Right. So this is a very easy experiment. So you have a material A, you put the material A into this tank, and we want to transfer. This is a chemical reaction. We want to make chemical material A and change to a products. And the temperature here is 45 Celsius. Of course, you put the material A into this tank, and then every you have a heater. You heat up the material A to the 45 Celsius. And once you increase the temperature, the A material will change to products. And this is the conversion. You have a sample tap. You have a valve, right? You have a valve. You open the valve, the material will come out, and you have an analyzer. So you know how many A change to products. And this is what we call conversion. Conversion, for example, conversion 50 conversion is what? You have 100 A, and after 2 minutes reaction, the A will become 50. Product will become 50. Okay, so A in the beginning 100, for example. And conversion rate, if the conversion is 50, and after 2 minutes, A will be 50, product will be 50. This is what we call conversion, right? Conversion. Sometimes with time, we say conversion rate. So, if I ask 10 students to do the same job, or if you are a student, you do 10 times this experiment, and are you sure you will get the same answer of the conversion, X? Are you so confident you will get the same answer? I'm sure you don't. Even though I asked 10 students to run the same experiment, I don't think the 10 students will get the same answer. So let's make the same example here. We call it rounds. Round 1, round 2, round 3, round 4. That means one student do 10 times experiment, or 10 students do the same experiment. For 10 students do the same experiment. So round 1, the conversion rate, conversion will be 67.1. Round 2 will be 73.1. Round 3 will be 69.1. Blah, blah, blah. And you have 10. So can I ask you, which student get the right answer? Which one? Nobody. We don't know. We don't know which one is the right answer. All we want to know is what is the average of these numbers, of these 10 numbers. So let's plot. So we have round 1, round 2, until round 10. So the round 1, the conversion rate will be 67. Round 2 will be 71, something like this. So how are you going to express these numbers? So why round 1 to round 10 are different? There are many factors, right? As I just told you, why difference? The first one is 67, the second one is 71, the third one is 71. The second one is 73. So that means I have 10 students. Student 1, when he measures, might be temperature is 45. But student 2, when he measures, temperature might be 44.9, something like this. Because what? Because it depends on your measurement, right? It can be 45.1 or it can be 44.9. So temperature will be different. So X change, conversion rate change. How about another factor? Sampling time. If I ask you to open the valve at 2 seconds, after 2 minutes, you start to run. The student A might open it at 2.01 minutes. Okay, student B might open it in 1.99 minutes. That's the difference. So you got different numbers of conversion rate. How about analyzer problems? And an analyzer might have a problem. You need calibration. Okay, so what's the true number of this x? As I just told you before, there are 10 numbers. There's no true number. We don't know the true number. But if there's no true number, how can we express these 10 experiments? How can we estimate of the true value of x? So which one? From round 1 to round 10, which one? No, you don't. So all you can do is you do the average. You do the average. So you got average, you have sample means, arithmetic means, and you got this number. I'm sure you learn this when you are in junior high school, right? Even in the primary school. Right? You do the average, you put 10 numbers here, you divide it by 10, and you got the average. So this is one way to express the number. In this case, it's conversion, right? Conversion rate. Okay, so first point is you do the meaning, you do the average. And the answer you got is 69.3%. So true value, nobody knows. But we can express this is the measure. This next one is the measure value. The third number you can get is arithmetic means, which is 69.3. And normally, I'm sure you will use this number to express these 10 numbers. So if I ask you to do 100 times experiment, or I ask 100 students to do experiments, and of course you will get a better results. You will get the better results to the approach to the true value, right? Okay. So apart from average or arithmetic means, do we have any way to express the number? Yes, we do. Okay, this is the sample variance of the scatter data. So how does data different? How do we express the data? Is this good data or is this bad data? So let me make an example here for you. If I ask 10 students to do the data set 1 and ask another 10 students to do the data set 2, and these two sets, set 1 and set 2, they got the same arithmetic means, they got the same average number. This is one like this. This is one like this. So could you tell me which data set is better? Data 1 or data 2? These two got the same average number, arithmetic means. Which one got the better one? I'm sorry, this is a bad example because, first of all, you need to take a look at the scale. The scale, this is 66, this is 74. This is from 0 to 100. When you look at it, roughly, you might tell me, well, Professor, this is a better answer because this sample is all the points are very close to the same level. So you got a better one. But I want to tell you is this one, the scale bar, the scale is different. So basically, these numbers are same as this number. So please be careful with this scale. Okay, be careful with this scale. However, I want to tell you another set. This set A and set B. Again, I also asked 10 students to do the set A, another 10 students to do the set B. And these are the numbers I have got. So which one is better? Set A or set B? I mean the quality of the student. Set A or set B? You know, these students, obviously these might be better students, right? They do experiment more carefully. So they have the same, almost the same level. They got the same answer, but this is too wide. So scatter, we have the same scattered data and the same, this scattered data get the same arithmetic means. That means average is the same. Okay. However, this is the way to find out which set of data is better. For example, if you say this one is good, better than this one, yes, this is right. However, as an engineer, I might ask you, how good is this? How bad is this? Okay? You might say, well, I say to you, let me make an example. No, I think I forget it. Let's forget this example. So, this is called qualitative. So if I ask you which one is better, you say, oh, Professor, set A is better than set B. You got the right answer. But I want to tell you is I am not happy with this answer. I will further ask you how good and how bad. So you need to tell me the number. As an engineer, it's very important to tell people that qualitative answer and a quantitative answer. Okay, so so this is the quantitative answer we need to find out. So obviously, you know, set A is better than set B, and how good and how bad is the set A or set B. So if you want to do the quantitative analysis, they have three methods. First is the range from the maximum to the minimum. The second one, we do it using a mathematical method which we call sample variance. The third one is a kind of modification of a sample variance. We call a sample standard deviation. So these three can tell you the number, how good they are, how bad they are. Okay. So let me start to talk about this. First one, range, right? Again, the set A and set B. So we need to find out the range, which is maximum and minimum. So in the set A, the maximum is 72% here. And the minimum will be this one. Minimum will be 68%. So the maximum minus minimum will be 4%. So the range will be 4%. So you can express, well, Professor, set A is better because in terms of range, set A has only 4%. But set B is more than 4%. Is 43%. Because the maximum is 95. So minimum is 52. So set A is better than set B qualitative. And set A has 4%. Set B has 43% quantitative. Okay, quantitative answer. As an engineer, you want quantitative answer. Okay, you don't want qualitative answer. Otherwise, you go to social science, you go to literature college. Okay. Okay, so the second topic or second expression to tell you the how quantitative answer is called sample variance. So as we use the data set B here, so I'm sure you know this is that if you know the average, which is the number one data minus average bracket power 2, and then plus what? Number 2 and you have average, right? Number 2 minus what? Average of the number, bracket power 2. Why we need to do this? Because there's a plus and minus. If you power 2, if you square it, use the square bracket, you understand that you will get all the positive numbers, so that it makes sense, right? I'm sure you learned this in your college, in your high school, right? Have you learned this number? Have you learned this equation in your college, in your high school? Have you? You do. You don't. No, you don't know. Okay. Anyway, okay. I don't need you to remember these equations, because once you do this, it's just type standard variances in the Excel, in the Googles, you will get this equation. But I want you to know the meaning of this equation. Okay, so the answer is that if the sample variance decrease, the data scattering decrease. That means it's better, right? Obviously, if this number is small, you got the small numbers. That means what? That means scattering is small, right? If this scatter is big, then you got a number big number. Of course, standard sample variance will become big. So if the sample variance is increased, data scattering will be increased. Okay. Next term is sample standard deviation. That will be compared to the previous one, sample variance. You just have a root, square root. That's it. You do the square root of the equation of the sample variance equation. Again, if the standard deviation decrease, the data scattering decrease. Right. So let's take a look of this example. The x-axis is run. How many runs? Like run 1, run 2, run 3, and obviously, probably let's say run 50 in this case. X, it might be conversion rate, for example, 50%, 90%, 70%, for example, like this. So first of all, you got an average, right? Arithmetic average, or arithmetic means x over bar here. Okay, and then you have numbers. N is numbers, right? Numbers. Like for example, here is about 50. X is each one, like 67, 70, 90. This is X. And X means what? X means that arithmetic means, right? So you have 3 these numbers. You can do the calculation of sample deviation, standard deviation X. So this is the expression of these data. Ladies and gentlemen, X equal to X over bar plus minus N times standard deviation. This is the expression of these numbers. So what is X over bar? X is this one, right? X is these numbers. X over bar means what? Arithmetic means N is a digital number. Is a digit 1, 2, 3, 4, 5. Okay, times what? Standard deviation. So what we call this is error limits. Error limits. Okay. Right. So you know now you know how to express a scatter data using arithmetic means and error limit. Okay. So in a typical random variables, normally it's like this. You have 50 runs and you got maximum, minimums, and something like this. But however, in generally speaking, about 99% of the data will be in this range. X over bar standard arithmetic means plus minus 3 standard deviation. Almost 99%. That means only one data out of 100 data is not in this range normally. Okay? And then how about 2 standard deviation? How many percent? Normally it's about 88%. Well, the data will be between 2 standard deviation, plus minus. And then if you narrow down 1 standard deviation, that's about 2 out of 3, 2/3 of the data will in the scope of the x over bar 1 standard plus minus 1 standard deviation. Okay, so this is a difficult random variables. I don't need you to remember this, but this is the kind of knowledge you need to know. 3 standard deviation will be include about 99% of the data. Okay, 2 standard deviation will be about 88, and 1 standard deviation about 2/3, 2 out of 3. Our data will between this 1 standard deviation. Okay, so let me give you a number. Now, if you have x, which is 48.2 plus minus 0.6, you might ask, well, Professor, 0.6, it can be what? If you plus 0.6, it can be 48.8. Or it can minus, right? It can be 47.6, for example. And if I ask you, how many standard deviation of this? 1, 2, or 3? Which one? You don't know. So you need to find out, or you need to make a definition for this. So the midpoint, 48.2, is the mean value of the data. Okay, arithmetic means for the error limit here, 0.6, it can be what? It can be range of the data set. That's what you need to define. What is 0.6? It can be range. It can be 1 standard deviation or 2 standard deviation. It can be 3 standard deviation. That depends on what you define or what you get this number. Other possibility can be really occur. Anyway, the important thing is normally we use this number as standard deviation. Okay? So make clear what error limit means. Once you get this number from somebody else, from somebody you need to ask him, what is the definition of 0.6? Is that 1 standard deviation, 2 standard deviation, or 3 standard deviation, or other possibilities? Right. So this will be the question before we end of this lecture today. So this is an example of 2.5-2. It's called quality assurance. We call QA. There's a factory. You know, factory makes chemicals, makes products, whatever. And then this factory produce 500 batch pigments per week. Okay, it produces 500 batch of the pigment per week. And of course, this 500 need to go to QA before you can sell it out, right? Sell it to your customer. Okay, so however, you might find some of the product which is not good. The quality, you cannot pass the QA, quality assurance. So you need to waste these products, this batch of the products. So the rejection is that if you have a wide batch week, then you need to think of something wrong with your factory, right? Because you are losing money. If this rejection of the bad batch is too much, for example, if you have 500 batch, you got 400 batch which is not good, which are not good, you need to return. So you can only sell 100 batch of the pigment out, and you lose money, right? So you need to think of what's wrong with your factory. Okay, so you need to define what is why before you continue to manufacture the pigments. Okay, so if you have enough good batch, then you can accept, you can continue to do the production. So as an engineer, you need to find out, you need to know that this is the data. You know, it's like artificial intelligence. You need to train the factory first. AI, right? AI, artificial intelligence. You need to have a raw data. And then once the raw data run the test, run the artificial intelligence, and then you need to tell him what's good and what's bad. And you need to get an answer. So this is week 1 to the week 12. Why means that the 17 batch no good products. 27, 18, 18, 23. Okay, 19 batch which is no good. So you got 12 weeks and you got these Y numbers here. So if you are a manager, if the 13 weeks come out, Y is 40. You got 40 here. 40, which is much worse than this one, right? Much worse than these numbers. Then what happened? You want to continue to do the manufacturing, or you want to shut down the factory to check what's wrong with your factory. So the technician might ask you, you know, the technician who is working on these factories will ask the engineer, what can I do? Should I shut down or should I continue? And as an engineer, you need to make a definition. So if you tell the technician, say that if the mean average is less than 3 standard deviation, you continue to work to do the production. If this is more than 3 standard deviation, and you need to shut down the factories to do the checking in order to have a better yield rate. Okay? So answer is that, okay, engineer say, well, 3 standard deviation. And how do you do the calculation? So why is Y? And then you need to shut down the factories. So how do you do the calculation? If you do the arithmetic means, right, of these numbers and put it here. And of course, you know how to do the standard deviation with these numbers, right? And you times 3, and you will get this number. Let me repeat this again. You have 12 numbers here, right? From 7, 17, 27, 18, 18. You have 12 numbers here. You know the arithmetic means, right? Which is this one, Y prime. And then you know how to do the standard deviation calculation with these 12 numbers. And you add up, you times 3 times. So the Y prime is 19.9 of this average number. And the standard deviation is 2.8. Standard deviation is 2.8. So if you put this here, the answer is what? Y equal to 28.3. But you know this is the integer number, right? Integer numbers, there is no 28.3. So let's think of 29. So as an engineer, you tell technician, well, once the number come out as 29, you shut down. Okay, and then you shut down the factory. You started to check what's going on. So, of course, why if this 40 at the 13 weeks is more than 29, right? So the factory need to shut down. Okay? However, if you want to make money and you want to be strict, like Tesla, you know, Tesla is the boss of Musk. Elon Musk, he's very strict. He said, no, I don't want 3 standard deviation. I just want 2 standard deviation. So what's the number of Y? Okay? So number is 26. So once the 13 number, 13 week, 14 weeks, 15 weeks, the number is more than 26, the factory needs to shut down. Okay. So this is the answer. I just tell you, please do a quick calculation. So the conclusion of this 2.5D is that you know the raw data, you know the maximum data or minimum data, you know the arithmetic means, and you know the standard variance and the standard deviation. Okay, and this is the expression of the data. X equal to X means plus minus error limits. Error limits can be maximum, right? Can be maximum, can be um, one standard deviation, two standard deviation, or three standard deviation. Right. So I think I will stop here, and we will move to 2.6 next week, Monday. Okay. So that's it for today. I hope you enjoy the lecture today.